Yep, what could possibly be inside this mysterious package? I guess we'll find out soon, as today I will show you how to wire your DIY pen plotter using 28BYJ-48 stepper motors and a servo up to an Arduino in order to get everything running. Personally, I'm actually going to build a custom controller board for this thing, kindly provided by PCBWay, the sponsor of this video. We're gonna install everything, wire everything up, including limit switches, which we haven't even talked about so far. It'll be amazing. Jumping right in, we have the Arduino Uno clone controlling two 28BYJ-48 stepper motors via some ULN 2003 Darlington arrays, as well as a standard 9-gram RC servo to raise and lower the pen. And we also have these teeny tiny little limit switches. Now, to connect all these things together, we first need some kind of schematic. And here it is! Yes, it is as simple as that. But wait, before I just give you the schematic, I first need to teach you how to figure these things out by yourself, so you don't need to go to some YouTuber's comment section whining about your shit not working like some 3-year-old brat in kindergarten. Starting with the most disgusting part of the build, called firmware. Honestly, if you haven't thought about what firmware you're going to use before beginning to build anything, then you're not an engineer. Sorry to break it to you. Either way, most DIY pen plotters with unipolar steppers, such as the 28BYJ and a servo, run on a single custom version of GRBL modified by 3 people a couple of years ago. The first one, Robotini, converted the pin for spindle speed control into the servo control, and as he clearly states here, pin 11 connects to the servo, as well as listing all the commands needed to control it. These are important things we need to take note of. Then, a couple of years later, Costi CNC here created another offshoot to make stock GRBL work with unipolar steppers, which was later merged with Robotini's version by Rizzivo. This is the build we're going to need, and as you can see, all the connections for the stepper motors are noted in the README. Subsequently, we can perform a simple Google image search for GRBL CNC limit switch, look for the one most appropriate to our situation, which in my case was this one, and we have all the information needed to conclude our schematic. We just need to combine everything, and this is the result. I deleted the limit switches for the Z-axis since those are unnecessary with the servo, and also reduced it to 1 end-stop switch per axis, because 2 would be kinda overkill. It's just a pen plotter after all. Now, if you don't want to go the extra mile of designing an entire custom controller board like I did, you can just stick the Arduino and the stepper motor drivers onto a piece of MDF, soldering wires back and forth to make the necessary connections. That's a totally valid approach, but since I love making things as difficult for myself as possible, I just had to make my own controller. And to fully understand how I ended up with this probably not so mystery anymore package, we need to travel back in time a couple of weeks to where it all started. So the idea of the schematic stays pretty much the exact same, except I want to put everything on the same board. And while I could make some kind of shield that stacks on top of the Arduino, very much like the RAM's 1.4 boards, I don't like that. It's messy. I want to take all the components on an Arduino and plonk them on a fresh board alongside the Darlington chips and whatever other miscellaneous components, resistors, capacitors we need for the limit switches. This also allows me to somewhat simplify things by getting rid of certain components that aren't needed in this specific application, like the entire second power rail with its own little voltage regulator and the little op amp down here. And then it was just a matter of downloading KiCad and designing it. Worth mentioning, this was actually my very first time designing a circuit board on the computer. Or actually, my very first time overall ever designing any circuit board. Either way, after 2 weeks of working on it in my spare time, this is what I was left with. Here's the schematic, and while I'm not gonna bore you with details, it's basically the same thing I showed you earlier, but integrated with a couple of unnecessary components removed. Then we have the board layout, not much to say about that, other than I'm not a pro at routing tracks. And finally, here's what the render looks like. Yes, very promising indeed. On the back, or actually on the top to be precise, we have a cool name printed in silkscreen along with my logo and a whole bunch of LEDs around the perimeter to create a fancy effect. Funnily, the logo of the board name alone took me half a day, so you can probably guess how long the rest took. It's actually insane how big a percentage of the work goes into the digital design step nowadays, even in the DIY sector. With all that taken care of, hopefully without making a terrible mistake somewhere along the line that even slipped through my double and triple checking, It was time to place the order on PCBWay's website. Roughly 10 days later, this arrived in the mailbox, which brings us back to present day and the imminent unboxing. Of course, in here there isn't just the circuit board I designed. Basically, since we're an influencer, they included a whole bunch of merchandise as well for us to decorate our workshop with, half of which is actually really amazing and very useful. Oh my god, this will be the first time in my life touching a circuit board that hasn't all the components already put on it. And here goes nothing. And wow. Here we have the PCBWay ruler. Then we have another board, which I don't know what it is. Wow, these are footprint boards. They're very, very useful. Oh yeah, this is the PCBWay logo printed in SLA resin printing. Also, first time ever touching a 3D printed part. It'll be interesting to see what the surface quality is like. And lastly, finally, our boards. Oh my goodness, they are even vacuum sealed. And here they are. Oh my god, this is so nice. Much nicer than I ever needed, to be honest. This is so nice. Look at that. And here's the back with my logo. It's so wonderful. As you can see, my choice of the white silkscreen was perfect because it is in fact an orangey yellow, or actually rather orange than yellow, but white and orangey yellow looks perfect together, I think. Then we have the other boards, just as nice except in matte black, and they are footprint references. So basically you place a component on there to see which footprint it has, and I think designing circuit boards, this is going to be very useful. The amount of detail on the SLA print actually surprises me. I didn't think it would be that precise. I expected there to be visible layer lines on the print, but I can see almost none, except here on this very sharp corner. I guess SLA resin printing isn't as crap as FDM printing. So yeah, this is really insanely nice stuff. I must admit, I'm so used to working with trash and recycled materials, using new stock already feels kinda weird, but having a bunch of circuit boards custom manufactured just for me to use feels outright wrong. For me, they should have at least included some manufacturing errors. So yes, this board is called Chronic Plot Hole. Why? Well, obviously because it's supposed to plot the whole thing, but also just for kicks and giggles, kind of a pointless reference to the actual word plot hole, although I don't think it's got anything to do with my pen plotter. I just thought it was funny. It is designed to screw right into the corner on the y-axis, therefore the cutout for the feet, which actually makes me realize my very first mistake, being that these feet aren't actually all the way in the corner, but slightly offset, which means I physically can't get the board all the way into the corner to make use of the other two screw holes. Oh well, that's an easy fix. If it's the only mistake I made, I'll be lucky. I just need to reattach these feet 12mm outwards. Problem fixed. That's more like it. But now we should really start gathering components to populate this board, which gives me the perfect opportunity to try out my brand new DIY lighting and filming rig over my electronics bench. So like I said, most of the components we're going to use are already on the Arduino. Yes, I'm actually going to take all the components off of the Arduino to put them on my board. Why? Because buying a single ATmega 328P microcontroller is already as expensive as buying an entire Arduino, and needless to say, many of the other components we need are on the Arduino. Then we're obviously also going to steal the two Darlington chips from the stepper motor drivers, along with the connectors used to plug in the steppers, ditching the rest. Since we ditched all those through-hole LEDs on the stepper motor drivers, we need some more surface mount ones, and I'm gonna salvage those from an old Wi-Fi router and cell phone. Each of those LEDs needs a resistor, and because it's exactly 8, I decided to use 2 of those SMD resistor arrays I have in my collection. I also need a random salvage tantalum capacitor and a different reset button since I couldn't find an appropriate footprint for the shielded one on the Arduino in KiCad. That should be pretty much about it. I'm gonna start by transplanting the most obvious capacitors and resistors first to liberate space on the circuit board for the more challenging removal of the chips. And it definitely looks like we're off to an awkward start. Yes, this is a lot of SMD hand soldering. I'm using my bifurcated SMD soldering tip to remove the components and 0.5mm lead-based solder to put them back on. Size-wise, all the small components on the Arduino have an 0805 footprint, which means at 2mm length they are still quite easy to work with. For comparison, the decorative LEDs I'm going to import from those scrap PCBs are all 0603. A good pair of quality tweezers is pretty much a necessity when working with those and everything below on the scale. Now we're pretty much done with everything easy to remove from the Arduino. For the rest I'll have to use the heat gun. Let's switch to the dedicated 0603 desoldering tip and 0.3mm solder to tackle those decorative LEDs. Yeah, this solder is lead-based as well, or at least it's supposed to, though I'm very skeptical of that claim considering the suspiciously high melting point and dull solder joints. Maybe I shouldn't buy the cheapest solder from China I can find, as it tends to be mislabeled quite frequently. There are only 4 LEDs of the same color on the Wi-Fi router, which means I can't afford to destroy a single one of them during desoldering, lest there won't be enough left for my controller, but unfortunately I did exactly that. I hate when these things happen, because now I have to take my other 4 LEDs for the Y-axis from another, even older cell phone motherboard, something I didn't want to do originally, because these are a different shade of orange instead of green like from the Wi-Fi router, as well as a totally different brightness. These will look shit together, especially on the yellow PCB. Maybe I should have used brand new green LEDs for both axes right away, since I do have a roll of those kicking about, but then it wouldn't be mostly made from trash anymore, which is basically my primary goal. Either way, they seem to work alright, though I might still swap them for some different ones further down the line. Okay, moving on to the chips and multi-pin through-hole components. First, I'm going to wet all the pins with lead-based solder, which has a lower melting point to hopefully prevent having to apply too much heat and potentially frying the microcontroller with the heat gun. Then it's basically just heating it up from below and waiting till the components can literally be picked off the circuit board. Same thing with the 2 stepper motor drivers, except I removed all the unneeded LEDs beforehand to avoid accidentally killing them. Now we have all the remaining components we need, we can add them to the board as well. I cannot stress how much I love these reverse action tweezers. They are so insanely versatile because they can hold SMD components for you without needing to be pressed all the time. Plus, they can act as a clamp like you see here till the component is completely soldered into place. Also, because they are so long and thin, they make it a lot easier to pick components out of the parts organizers I store my components in without inadvertently obstructing my own view with my big clumsy hands. Honestly, I would put these on second place of the top 10 most fundamental tools to get if you want to get into electronics or pretty much anything dealing with delicate small parts. Last but not least, the USB port. The way this fits is so satisfying. And I'd say, Chronic plot hole is finished! Now, this all looks very nice and good, but the real question is, does it actually work? Place your bets now in the comments down below, as I have never made even a medium complexity circuit board that was functional right off the bat. If this one actually is, it'll be a sensational first. If it is not, I think it's safe to say I'll be in for a very bad time. Another thing I did before desoldering all the components from the Arduino was uploading this test sketch to it, designed to cycle through all the decorative LEDs. That way, once I plug the finished controller into the computer, we're gonna find out whether it works or not pretty quickly based on what these LEDs do. And also, of course, we're waiting for the bing 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 noise from the computer, recognizing chronic plot hole as a USB device. I went ahead and connected everything the exact same way it would be connected with everything built into the plotter. That is, we have two push buttons to imitate the limit switches, one servo for the Z-axis, as well as a 5-volt input from an external power supply. Stepper motors aren't needed in this test because basically the decorative LEDs are connected to the exact same outputs as the stepper motors would be, so once these LEDs light up, the stepper motors will be driven. And I think it's time for the moment of truth. Let's plug this power supply in, at which point nothing at all should happen, and see what happens. So far so good, nothing did happen. Now for the USB. And this is actually the 5-volt that powers the microcontroller. Here we go. Oh my goodness. You're not telling me this works? No, it doesn't work. Of course, why should it work if it could just as well not work? Oh my goodness, these LEDs should now start sequencing through, but they don't, obviously. This LED is lit very dimly, which is also not good. Oh my goodness, if I press one of these buttons, nothing happens. Arduino Uno port is going to do anything. So the computer obviously recognized the USB chip, but then nothing else happened. I do not get the USB port to select. Oh my goodness. That's not a good sign. Let's use the other USB port. That is not good. What is going on? Yeah, of course. Why break a tradition of not working circuit boards if we could just as well not break it? Darn. Of course it doesn't work. Now, I just hope it didn't fry any of the components, because then I'll have an even bigger problem. No, I hate this! What on earth did I do to deserve this?
The very next evening.
Guess what? It actually works now. As you might have expected, I screwed up big time. But the one to really sink the ship and quadruple the amount of work needed to fix it was actually KiCad. Thanks, KiCad. So for the repairs, I actually had to butcher the nice circuit board, which may be a shame, but at least it works now. Starting with the smallest mistake first, this teeny tiny tantalum capacitor was actually soldered in the wrong way around. And because it is a polarized capacitor, it basically shorted out the entire 5-volt USB supply rails coming from the computer. Luckily, there's a small PTC fuse in line with everything, which regulated the current down to safe levels. And why did I put the capacitor in the wrong way around? Well, on every goddarn diode and electrolytic capacitor, there's a stripe indicating the negative pin. So why on earth does the stupid stripe indicate the positive lead on a tantalum capacitor? Next mistake is a little more embarrassing because it actually made it through my double and triple checking. Basically, I command all these LEDs to ground instead of 5 volts. Thing is, the transistor array doesn't actually put out 5 volts on each of these lines, but switches them to ground instead, practically rendering the entire chain of LEDs useless. I ended up fixing that by breaking the connection to ground and using enameled copper wire to connect them to 5 volts instead. However, this is just the tip of the iceberg. After all, decorative LEDs aren't exactly vital to the functioning of the circuit and could, if desired, be omitted completely, just like the capacitor could be turned around. But for the third and by far biggest screw-up, I am not willing to take the blame. It was definitely not my fault. For whatever reason, KiCad got the footprint for the microcontroller completely messed up, such that the pads on the PCB don't correlate to the respective pins on the chip. Basically, it was connected seemingly at random, with 5V and ground feeding into these two crystal pins, while the actual VCC input got hooked up to the Darlington stage. There was literally no way the chip could ever have worked in this configuration. Fortunately though, this did not kill the microcontroller, possibly even due to the capacitor shorting out the supply rails before much current could get into the ATmega. Either way, the only solution to fix that, other than maybe getting a whole new set of boards made, was soldering 21 pieces of thin enameled copper wire to the required pads and putting the chip on top by routing every single wire to the correct pin, which for the most part was located on the opposite side. This makes it look a lot neater than it actually is, because all the crazy rat's nest is safely tucked away underneath the chip. I even feel like I got this soldered pretty quickly, as it only took like 6 hours. Having discussed all that, let's see what it should have done upon being plugged in earlier, after which we can finally start installing it on the plotter. So let's go. Plug it in, a nice noise, faking a boot up sequence with all the LEDs lit, and it starts cycling through. Now if I press the X-axis button, all the X-axis LEDs light up and the other ones continue cycling. If I do the Y-axis button, same thing happens with the Y-axis. Then, if I open the serial monitor, we get a nice boot up message, and it asks us for an angle to put the servo in. I'm just gonna type 92, well, go with it, and it goes to 92 degrees, 52, and there we go. It works perfectly fine, as you can see. And I can also press the reset button here. It resets manually. There we go. This is what it should have done, and quite obviously didn't do. Installing it on the pen plotter is literal child's play compared to all the hard work of making the board. It simply screws onto the Y-axis from underneath using a couple of salvaged panhead screws, then the steppers plug right into the controller and we're halfway done. Next easiest thing is the power supply, and for that I'm simply going to use this generic USB charging lead with the broken micro USB side snipped off, so now we basically just have a cable with a standard USB plug on one side. Inside this cable there are 4 wires. The white and the green one can be snipped off at slightly different lengths to avoid shorting them out, whereas the red and black one need to be soldered to the controller. For the strain relief, I made this little piece of hardwood, which basically clips onto the cable and gets pinched down by the last missing screw, hence why that screw was missing in case you noticed. Installing the limit switches is actually the exact same process, whether you use a fancy custom controller board like I do, or what I'd recommend if you want to avoid headaches, the discrete Arduino and stepper motor driver approach I showed you in the beginning of the video. I just connect my switches straight to the designated inputs on my board, which basically equals connecting them to digital pin 9 and digital pin 10 of the Arduino. Just keep in mind you need to add the capacitors and resistors shown in the schematic. I don't need to do that because those are already included on my board. Like I mentioned before, I'm going to use these super tiny limit switches. Of course you have many options, most of them are overkill, but these tiny ones should do the trick just fine. If you're wondering where you can get these, they can be salvaged out of these obsolete CD player thingies. In there, they are actually used as limit switches for the playhead, which is basically where I got the idea. For the wiring, you can basically use whatever you please, which means I'm gonna use the crappiest headphone wires I have. This stuff is basically just 2 very thin enameled copper wires inside some rubbery insulation. And this is where I crack out the hot melt glue gun, cause don't get me wrong, hot glue is great, but only when applied correctly. And what I mean by correctly is, this is not the kind of abomination that calls itself a life hack channel. Here at Chronic Mechatronic, things need to look neat and well made, whether they contain hot glue or not. Same goes for the x-axis. Don't get fooled by the fact that I just seem to stick it on without measuring. The front of the switch is in line with the right edge of the metal bracket, so the carriage pushes the switch before crashing into the solid metal. Some tidying up and cable management later, this is what it looks like. As a general rule of thumb, to prevent interference, you should not run the cable for the limit switches in parallel with the motor wires, although this little crossing here shouldn't hurt. Next, to make the y-axis actually engage its limit switch, I screw on this little piece of plywood to push the button. Last thing we need to connect is the servo, and for that I'm going to use servo wire, left over from a radio-controlled airplane I built 10 years ago. This time though, I solder one end of the cable to the controller first, then do the cable management all the way to the end in order to cut it to the exact length I need, before soldering on the pin header to which the servo gets connected. That's one small plugging in of a connector, one giant project ticked off the list for this YouTube channel. Can you believe it? After 7 months, the pen plotter is finally complete. Well, at least for the most part. Let's run one last test to see if these switches actually work. This one does, and the other one I have to do by hand or else we won't see anything. So here we go, it works as well. I can also hear a faint ticking noise from the stepper motors, which means they're currently active as well as moving, although extremely slowly. The only things left to do with the plotter now are installing and subsequently setting up the firmware, as well as building the mystery engraver extension I've been teasing for what feels like ages now. Speaking of engraver, you might be interested to know that I recently purchased a 5-watt laser module, and no, I'm not going to put it on the plotter, even though that would easily be possible, because the plotter has a strict budget of exactly $0, and the laser module, not being sponsored, does literally not quite fit the bill. But don't worry, we're going to build a much more accessible, poor man's engraver in the last episode of this series. Gigantic thanks goes to PCBWay for sponsoring this video and sending these amazing quality boards. What a shame that my design was inherently screwed, making the other 4 copies of the controller board unusable without the extensive modifications I had to do to the one on the plotter right now. And it goes without saying, without PCBWay this video would have looked quite different as well, as we would have chosen the discrete Arduino and stepper motor driver approach, from which I would definitely have learned nothing along the way. Finally, if you arrived at this point in the video without skipping anything, congratulations, your attention span is that of a healthy human being. Seriously, as a content creator, I most appreciate people watching the entire video, since each minute of my video takes an entire day's worth of work, and anything skipped is literally my effort down the drain. Hope you enjoyed, and I will see you next time. Bye!